Hello everyone, this is Sarvesh, lecturer in civil engineering, Government Polytechnic, Station Kanpur. The course is reinforced concrete structures. Today, we are going to discuss the design of continuous beams and slabs as per IS 456-2000. After completion of this lecture, you are able to know what is meant by continuous beams or slabs and what are the difference between the simply supported slabs and continuous slabs. Then you are able to know what is the difference between the simply supported beams and continuous beams. And then you are able to know what are the advantages of continuous beams and slabs over simply supported beams and slabs, right? And before going to start today's lecture, I would like to just recap whatever we were discussed in last class. So in last class, uh, we were discussed about what is meant by T-beams and how to design the T-beams and how to calculate the moment of resistance of T-beams and what is the difference in calculation of moment of resistance of T-beam as compared to singly reinforced section. That means in T-beams, the moment of resistance is depends upon the location of depth of neutral axis. So based upon the location of depth of neutral axis, it has been uh, classified into three cases. That means if the depth of neutral axis is within the flange, it is similar to the thickly reinforced beam. And if the depth of the neutral axis is within the bed, right, then there are two cases. That means when the compressive stress is uniform throughout the thickness of the flange or not, it is not uniform. So that means if df by d is less than or equal to 0.2, that means the stress is constant throughout the thickness of the flange. If df by d is greater than 0.2, then it is not uniform. So in that case, you need to determine the modified thickness of flange, and according to that you can determine the moment of resistance. And then we were solved three problems on analysis. That means for the given section we have determined the moment of resistance corresponding to the uh, depth of neutral axis, right? All three cases we have done the problems. And similarly, at the end we were discussed about the design of T-beams. So in design of T-beams, we were solved two example problems for better understanding, right? So this is about we were discussing last class. Now coming to today class, and before going to the design of continuous beams and slabs, so let us just rewind what is meant by slab. Slab is nothing but it is a structural horizontal member carries lateral loads perpendicular to its plane, and the thickness of slab is much lesser as compared to the length of the slab, right? So it is a structural member which carries a lateral loads perpendicular to the plane, right? And what are the types of slabs based upon the support conditions? We all know that there are different types of supports, that means simply supports, uh, hinge supports, roller supports, right? All these things. So what are the different types of slabs based upon the support conditions? So we were in design of slabs, we have discussed uh, the different types of slabs based on support condition as well as the load distribution. That means the longer span to shorter span ratio. Here, just I am classifying based upon the support condition. So it is simply supported slabs, uh, continuous slabs. Another one is the cantilever slab also, where if the slab is extended from the support, that means porticos or let's say uh, sunshades. All these slabs can be designed as a cantilever slab, right? So simply supported slab means the slab is rest on two supports is termed as simply supported. Continuous means if the slab is continuous more than two supports is termed as continuous slab. That means if the slab is raised on more than two supports, that means let us say for example, if I see the cross section and the slab is like right, that means it is extended more than two supports. Then in this case, this type of slabs we call it as continuous slab. If you see in the plan, this is one support beam, let us say, and this is another like. So this is the general happen. So we cannot construct a simply supported beams or slabs, right? So generally in practice, we will consider as a continuous. We cannot construct part by part, right? Until and unless specific cases. So this is called as continuous slab. If the slab is continuous more than two supports. Yeah, there is this is for slab. Right? Next, coming to the beams. Beam is nothing but we all know that it is a horizontal structural member which carries the loads perpendicular to its length, right? And it transfers to the column. So as I told earlier, the load transformation happens from top to bottom. That means first we'll take the slabs to beams, beams to columns, columns to footings, footings to soil. The construction will start from bottom to top, right? That means exploration of soils, footing constructions, columns, beams, and slabs. So beam is a horizontal member which transfers the loads, lateral loads, which is perpendicular to its length. And based upon the type of supports, the beams are classified into different types. That is simply supported beam. That means if the two beam is resting on uh, two supports, simply supports, then we call it as a simply supported. Fixed beam, that means if the both ends are fixed, so suppose this is a beam and both ends of the beam is fixed. This is fixed beam. And coming to cantilever beam, we'll discuss what is cantilever beam. So one end is fixed, the other end is free, right? Yeah, this is a cantilever beam. So what is meant by proper cantilever beam? Proper cantilever beam means there is a support at the free end. There is a prop at the free end, right? This will call it as a prop cantilever, right? Overhanging beam means if the beam is supported on two supports and extended to at a certain end, right? So this will call it as a overhang. Right? Then what is a continuous beam? Continuous beam is nothing but if the beam is supported more than two supports. That means there is a so this is the total beam and it is a See here, if the beam is supported supported on more than two supports, then we call it as a continuous beam, right? This is called as continuous beam. Now, just to move this thing so that, right. The continuous beam which rests on more than two supports, more than two supports is termed as continuous beam, right? Due to this, the bending moment developed within the beam is different as compared to simply supported or cantilever. Just I would like to show the uh, a small bending moment diagram. I think you already known in your theory of structures, right? The continuous beam bending moment diagram. So the bending moment diagram for continuous beam like this, right? It will, right? So this is the shape of bending moment diagram or bending diagram of the continuous beam. So here there are two types of bending moments developed within the continuous beam. So this is called as sagging bending moment. This is called as hogging bending. That means positive bending moments and negative bending moments. The positive bending moments occurs at the mid span of the beam, right? So this is the positive bending moment, that is sagging bending moment. Hogging bending moment occurs at the supports. These are all called hogging bending, right? That means negative bending moment. So from this diagram, it is clear that the positive bending moments occurs at midspans and negative bending moments occurs at the supports. So that is the hogging bending moments and sagging bending moments at the midspan, right? So due to this, the tension reinforcement provided at midspan is on bottom side and the tension reinforcement provided on top side at the midspan. Because see, why we are providing the reinforcement? The reinforcement is provided to resist the tension forces, right? So in this case, the tension is in the bottom fiber. That means at the midspan, the tension is on bottom fiber. At the support, the tension is on top fibers. Therefore, at midspan, the tension reinforcement is provided at the bottom fiber. At support, the tension reinforcement is provided at the top fiber, right? So that is the continuous beam reinforcement placement and bending moment diagram. So what are the advantages of continuous beams or slabs as compared to simply supported beams or slabs? So because see, the maximum bending moment occurred in continuous beams is much less as compared to the simply supported beam for same span and loading conditions, right? Because there are more than two number of supports are there, so therefore the bending moment is much less. And similarly, uh, this settlements, that means the deflection is also very less as compared to simply supported. And one more important thing is for the same span and section, the load carrying capacity of continuous beams is very high as compared to simply supported, right? And for the same span, mid-span deflections are less as compared to simply supported beam. And for the same span and depth of the section, the depth of the section required is very less as compared to simply supported beam because it is a more steeper. Therefore, the depth required in continuous beams is less as compared to the simply supported. And the mid-span movement is always less than the support. whatever just now I shown, the midspan moment is always less than the support moment, right? Hence, the weight of the beam does not affect the stresses, because at the support the bending moment is more, then the support will take care of all these things, right? And at the midspan the moments are very less, therefore you will get the very less depth, so therefore the weight will be reduced. And in continuous beams and slabs are much stronger and stiffer as compared to bending simply supported beams. So therefore uh, the continuous beams are very strong and stiffer as compared to simply supported. So these are the some of the advantages of continuous beams and slabs as compared to simply supported beams. Right. Now we'll discuss what are the behavior. That means what is the behavior of continuous beams and slabs. How they will behave. Right. So the behavior of continuous beams and slabs are different as compared to the simply supported beams, because in continuous beams the load combinations are to be considered absolute in order to obtain absolute maximum bending moment and shear forces. See, in simply supported beam, so we will directly apply the dead loads and live loads, right? So what happens in continuous beam? So if you see, suppose this is a continuous beam, just I'm drawing just for example. Sorry. Suppose so there is a continuous beam, right? Here we have a more than two. Suppose let us say for the example I'm taking only three suppose. So the maximum bending moment depends upon the combination of loads, various combination of loads, and one right. And suppose see here, due to the this load there is some reaction at here, and due to this load there is some reaction at this point. There is an effect at this point and there is an effect on this point. And similarly, due to load on this span, there is an effect on this span and there is an effect on this span. And one more thing is, so it is a continuous beam. So always there is some sharing, right? Some percentage of reaction or bending moment share to this support and similarly this support. And similarly, some percentage of resistance from this support will share to this support, and similarly for this support to this support. It is because it is a monolithic construction, and whenever you apply the load, the effect will share. The total beam will affect, right? So the maximum bending moment and shear forces are depends upon the load combinations considered in order to obtain the absolute maximum bending. That means whether it is a dead loads or live load. Suppose if you consider dead load here and dead load plus live load here, that is another case. And or dead load plus live load here, and this is only the dead load. So there are different type categories of combination of loads. So based upon your consideration, the maximum bending moment and shear forces will change. And one more important thing is the bending moment and shear forces at any section in a continuous beam depends not only on the type of position of loads in the same span, but also on the type and position of loads in the other span. As I told now, so because of this is a support, right? So due to the bending moment at this place is depends upon the loading combination and position of this beam, and the load and combination of loads on adjacent spans also, right? Because due to this load there is some effect here, right? And due to this load there is some effect here. Similarly for here and here also. So that means the maximum bending moment and shear force at any section is not only depends on the loads on the beam, it is also depends upon the load and type and load positions in the other span also. Right? So while designing, you need to calculate that effect also in continuous beams. And in the case of dead loads, all spans are loaded simultaneously, and this condition does not cause any problem, right? So does not pose any problem. So because self-weight is occurred simultaneously, it doesn't mean that one beam take the self-weight, other span will not have a self-weight. No, because the self-weight is simultaneously will act on the uh, uh, overall length of the continuous beam. So you have to consider at a time, right? But in case of live loads, so in case of live loads, different sets of spans may be loaded at a different time to determine the maximum bending moment and shear forces, right? Because you need to determine, see, suppose if this is a uh, beam and it is subjected to, let us say, four span, three span, one, three span, right? So to determine the maximum bending moment and shear force, so there are different combinations we need to try. So assuming that the self-weight is occurred on the total length of the beam, right? Next is the load combination, other loads, live load and other loads. First we need to apply the live load at here and here and determine the bending moment and shear forces. That is one combination. Next, you apply the live load here and only dead loads here and find out the uh, bending moment and shear forces. And then live load and dead load here and only dead loads here. That is another combination. All so these are the different types of combination. So to determine the maximum shear force and bending moment, you need to try all these possible cases, right? So these are all possible combination of load spans have to be considered in order to obtain the maximum forces. Now coming to the analysis of continuous beams. That is, continuous beams may be analyzed in two ways. That means two methods. So first method is method one, that is enter either by using the coefficients as specified in table 12 and 13 as per IS 456-2000, and this method is approximate and quicker method, right? So by as per IS 456-2000, a method is proposed for design of continuous beams and slabs for determining the maximum bending moment and shear force from table 12 and 13. And from this method, you can determine the maximum shear forces and bending moment. And it is clearly says that it is an approximate method, right? And there are other methods, that is method 2, by considering different combinations of loaded spans and plotting the envelopes after carrying out the desired redistribution. This method of analysis will be used for important structures, right? So just simply like that, in I think you were studied in your previous year, that is in theory of structures. So in theory of structure, I think it is in last unit. There is a method called as moment distribution method, right? I hope you all remember about the moment distribution method. In moment distribution method, what happens? Suppose this is a beam subjected to a different type of load, right? And based upon the stiffness of the member, some percentage of movement will transfer to this support and some percentage of movement is transferred to this support. Similarly, because it is if you apply the load, there is an effect here. Some effect is already some effect will occur in this beam also due to this load, right? So, in moment distribution method, you can transfer the some percentage of load to this support, and similarly, you will get some percentage of load movement from this support and from this support, and some percentage of movement for this beam, some percentage of movement will come from this support, and some percentage of movement will come for this support. That means it is a movement distribution. It distributes the movement for the related supports based upon the thickness of the member, right? So if you want to determine the accurate shear forces and bending moment, you can use another method, that is redistribution method. So for example, this is one of the redistribution method, distribution moment distribution method, and another method is also called as that is Khan's method. Some other methods are all there to determine the accurate shear force and bending. See here, the IS 456 is proposed some method. In that method, it is giving the coefficients for determining the maximum bending moment and shear forces, right? It is not giving any type of designs. So design is completely different. So, but to design that, you need shear forces and bending moments. To determine that shear forces and bending moments in continuous slabs and beams, it is giving some coefficient, right? So that shear forces and bending moments we can calculate by using another accurate method, right? Like that is moment distribution methods or harness method or any other desired distribution method you want to. If you want to use it, you can use it. Or another method is called as that is load substitute method. That is also a very famous method you can use to determine the maximum shear forces and bending moments in continuous slabs and beams. Right. So these are the two methods you can design the continuous beams and slabs. And one more thing is to determine the maximum shear forces and bending moments. It is very important to arrangement of the loads for getting the maximum shear forces and bending, right? So based upon the arrangement, you will get the maximum shear force and bending moment, right? That means in design a continuous beam or one-way slab, continuous slab, it is necessary to determine the maximum positive and maximum negative bending moments at critical section, right? Wherever the critical sections are there, at the critical section, you need to determine the maximum and positive and maximum negative bending moments and shear force. And at supports and midspan, that is at supports and midspan by considering the various possible load arrangement. As I told that, that means uh, this is this is a right three span. That means first obviously the dead load is present in all the cases at all the time. And first case is, let us say, live load is applied on these two and only dead load here. Next is here live load and only dead loads. Next here live load, these are only dead load. There are different combinations, right? See, we cannot say that if you apply total load, then you will get the max. It is not like that, right? So we will see all these things while designing or designing the continuous beams and slabs, right? So you need to try all these styles to get the and compare it and find out the maximum shear forces and bending. So that is the arrangement of loads to get the maximum shear forces and bending. Now coming to the general loads on beam consist of dead loads and live loads, right? So dead loads are permanent loads and occur overall the span while overall the lifespan of the member. And live loads sometimes may occur, sometimes may not be occurred, right? So live loads may or may not cover all the span. So therefore, the arrangement of live load is therefore required to be considered, which develops maximum moment and shear force in the peaks, right? So as I told just now, I told so live load, dead load is present in all the cases. Only you have to vary the live loads to get the maximum shear force and bending moment. Now coming to the it is a fact that it is not always the maximum load that produces maximum moment. No. So even a minimum load on one span can produce maximum bending moment in adjacent span in case of two span continuous beam. Right? So minimum load on one span can produce maximum bending moment on adjacent span of a two span continuous beam. Right? And one more thing is load is maximum when dead load and live load act together, while it is minimum when only dead load acts, right? And according to the IS 456-2000 class 22.4.1 makes following recommendations for arrangement of imposed loads for beams and slabs continuous over the supports. That means, so as per IS 456-2000, it is proposing the arrangement of loads, imposed loads for beams and continuous slabs, right? If you see in code as per IS 456-2000, class number 22.4.1, that is consideration, the arrangement of imposed load, that is a consideration may be limited to combination of, first one is design dead load on all spans with full design imposed load on two adjacent spans. That is first case. That means design load on all spans with full design imposed load on two adjacent spans. And second point, design dead load on all spans with full design imposed load on alternate spans. That means first you can consider first case is design load on all spans with full design imposed load on two adjacent spans. That means, as I told now, suppose if it is a two spans, two spans, it consists of minimum three spans, because this method is applicable for the continuous beams or slabs having minimum three spans. We'll discuss what are the limitations of the method, right? So before going to the just I would like to explain what is this one. So let us say you have a three spans, right? So first case we say that design dead load on all spans with full design imposed load on two adjacent sides. That means only dead load here and dead load plus live load, and this is also dead load plus live load. So this is one case. Another case is the design load on all spans with full design imposed load on alternate spans. Load on two adjacent. Design imposed load on two adjacent spans. And here it dead load on this is dead load on all spans, design imposed load on two adjacent spans. Here dead load on all spans with full design imposed load on alternate spans. That means suppose if you have a more than another spans are there, then dead load is on all spans and live load here, live load here, like this. Next one is live load plus dead load here, live load plus dead load here. This is only dead loads, right? So these two conditions may be considered in the design of continuous slabs and beams for as per IS 456 code, right? So next is the bending moment and shear forces at any section in a continuous beam depends on the nature and position of the loads in the same span on the loads on other span, right? So under the dead loads, all spans are loaded simultaneously. But in case of live load, several combinations of loading, different spans have to be considered to determine the maximum forces. Just now what we have discussed, right? And now coming to the as per IS 456-2000, class 22.5 gives the simplified coefficients to determine the maximum bending moment and shear forces in beams and slabs, which are continuous over at least 3 spans. However, no span should differ by more than 15% of the longest span. And the bending moment coefficients are given in table 12, and shear force coefficients are given in table number 13 as per IS 456-2000, right? So what does it mean? So as per IS 456-2000, to determine the maximum shear forces and bending moments, or to design the continuous slabs and beams, a simplified method is proposed, right? In terms of coefficients, that means maximum bending moment coefficients and shear force coefficients, which are presented in table number 12 and 13. But these values are applicable, right? These values are applicable if the continuous beam having a minimum of 3 spans, right? So as per the here, the minimum number of spans for continuous beams on slab should be 3, right? It should be 3 or more than 3. If it is 2, then this method is not applicable, right? The minimum number of spans should be 3. That means, so this is one, this is first one, this is one span, second and third. 1, 2, and this is third span. So minimum 3 spans are required, right? And one more important thing is, no span should differ by more than 15% of the longest span. What does it mean? That means, see, suppose if you have this is L1, this is L2, this is L3, for example, right? This is L1, let us say L2, L3, right? So what is the condition? Span should be, sorry, no span should differ by more than 15% of the longest span. That means the difference between these two spans should not be greater than the 15% of the longest span. That means as compared to these three, the longest one is L3, right? The difference between any two spans should not be greater than the 15% of the uh, length of the span of L3, right? In that case only these table values are applicable. If it is greater than, then this method is not applicable, right? That is what it is given in as per IS 456-2000, right? And these are the shear force and bending moment coefficients. And remember, there are different terminology used here for shear force and bending moment coefficient. That means, as I told, this method is applicable for having a minimum 3 spans, right? So just I would like to write down the different terminology. It is very easy if you understand the different terminologies. You can take the values and find out the shear force and bending. Let us say this is a total continuous beam, right? So these are the bending moment coefficients. So suppose these are the span moments, these are the support moments. So for type of load, that is dead load and imposed load, fixed. Dead loads and imposed loads are fixed. So in this case, the bending moment coefficient near the middle of end span, near the middle of end span. That means which one the end span? For in this case, this is the end span. This is also end span, right? So near the middle of end span means these coefficients, if it is a fixed, it will give the bending moment at this point, and right, this is the near middle of end span, right? Next, at middle of interior span. So that means, suppose if it is a dead load and live loads are fixed, then the bending moment coefficient at middle of interior span is 116. That means this is the interior span. These are the end spans. This is the interior span. So this value is used to determine the bending moment at the middle of interior span, right? And similarly, come to the support moments. So at support next to the end support, at support next to the end support, right? Suppose if you consider this one, right? So this value will give the bending moment at support next to the end support. This is at other interior supports. So this will give the next to the end support, right? So what is the next to the end support? So here support next to the end support. That means this is the support. Next to the end support is this one. So if you use this coefficient, you will get the bending moment at next to the end support, and this will also next to the end support, right? So if it is a, let us say another support is also there, then this will also next to the end support, and this will become as interior support, right? So if you use these values, you will get the bending moment at the next to the end support. That means this one and this one. Yes. So you have to take the corresponding bending moment coefficients and determine the uh, bending moments by multiplying with load and length, right? So similarly, you can calculate the shear force coefficient also, right? So these are the shear force coefficients. Let us draw again the diagram. I would like to draw for these spans for example, right? So here, dead load and imposed loads are fixed. Then at end support, shear force at end supports. That means these are the two or end supports. You will use the shear force coefficient, and you just multiply with load into yeah, sorry, you just multiply with what, the shear force. The coefficient shall be multiplied with the load only. So this coefficient is multiplied with load, you will get the shear force at end support. And coming to at support next to the end support. So that means this is the support just next to the end support. So this is the end support. Next to end support is this one and this one. Here you will get two bending moments, right? That means one is this side and one is this side. That means one is due to this one and one is to this one. That is called outer side and inner side, right? Outer side and inner side. You need to calculate both the shear forces, outer side as well as inner side. And for all other intermediate supports, you can use these coefficients to determine the shear forces, right? So if you solve a problem, then it will be easy for you to determine the coefficient, right? So for this, I would like to conclude this today's lecture, right? So this I would like to summarize whatever we were discussing about. So we discuss about the what is the difference between the continuous beams and slabs as compared to simply supported beams and slabs. That means if the supports are more than two, then we call it as continuous beams or continuous slabs. And what are the advantages of continuous slabs as compared to uh, normal simply supported beams and slabs? Because see, it is a continuous slabs, therefore the depth required is very less, and it is more stiffer and stronger as compared to simply supported beams. And later, then we will discuss about the what are the analysis and design concepts of continuous beams and slabs. That means whatever the method is proposed by IS 450,000 and 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 how far this method is applicable for different cases, and how the load is distributed in continuous beams. All these things were discussed, and how the continuous beams and slabs are behaves, right? And at the end, we were discussing about the codal provisions for determining the design of maximum shear forces and bending moments from the IS 456 2000. And also, we will discuss about the limitations of the method, right? That means the method proposed by IS 456 2000 is applicable only uh, for the beams having more than more than or equal to three spans, and the difference between the two spans should not be greater than the 15% of the longest span. So these two conditions we need to check before applying the IS 456 method for determining the bending moment and shear force factor. And based upon the factors, you can determine the shear forces and bending moment for different cases which are mentioned in the table, right? So for this, I would like to conclude this class. So next class we will discuss the design procedure and we'll solve some examples.